Okay. Evening, everybody. Good evening. Welcome to Burlington House, and welcome to the September evening meeting of the engineering group of the Geological Society. Before we begin, just a few quick housekeeping things. We are not expecting any fire drills or alarm tests this evening, so if you hear a continuous bell, it is real. People towards the front of the room are requested to leave the building by this door on my right-hand side, and people at the back towards the rear and out onto Piccadilly and right again into the Royal Academy. But given that you're not too many people here, we could probably all manage one door. Toilets, ladies and gentlemen, are both accessed through the door in the rear corner of the lecture theatre. A quick reminder that there is no smoking permitted at Burlington House. And please, a reminder to turn off or make silent your mobile phones before the presentations begin. A quick date for your diary. The next evening meeting of the engineering group is the 3rd of October. Back here at Burlington House, where Tim Blower will be of Mont McDonald will be here to talk to us on the geological influences on the Banjar hydropower dam in Albania. So the date for your diaries. So we are joined this evening by two speakers who are here to give us a presentation on the geotechnical considerations for the design and construction of Hinkley Point C new nuclear power station. Gemma Sherwood is a chartered geologist, currently working for EDF Energy as a senior geologist on site, and Mark Scorer is a chartered civil engineer with around about 10 years with Atkins and around about 5 on Hinkley Point C. There will be some time for questions at the end of the presentation, so please do store up any thoughts you have as they are going on. And without further ado, I will hand over to Gemma.
Hello, everyone. My name's Gemma Sherwood, and my colleague here is Mark Scorer, and we're here today to tell you about the construction of Hinkley Point C. So I was seconded in October 2016 to Hinkley Point C from Atkins. I was with Atkins for a year and a half while on the project, and then I've recently moved to EDF Energy, and I provide technical support on site as a part of the site surveillance team and also as a field geologist. So tonight's talk, we're going to give an overview of the Hinkley Point C site, including the geology and engineering geology, and the challenges we're facing on site. The construction and the geotechnical processes that we oversee, and when things don't go to plan, which many of you will know is quite common. Then Mark's going to discuss about the detailed design, including work packages and seismic qualification and Atkins digital tools. So just to give you a bit of information about Hinkley Point C and to demonstrate how important a project like this is, and particularly one of this scale, this is the first new nuclear build to be built in 25 years, and it's the first of its type, which is a European pressurised water reactor to be built in the UK. It's going to cost almost £20 billion to build, and it will generate 3.2 gigawatts of electricity, which will power over 6 million homes. It's going to take almost a decade to build, and it's going to be completed in 2025. So far, we've installed over 32 kilometres of ground nails in the slope protection. Now, I actually think it's more than that, because they're banding around the fact that you can go from the site to Bristol in the length of nails, which I think is about 42 kilometres. And we've also had 14,000 tonnes of rock armour delivered to site, and that's all come from South Wales. And directly below the foundations of the nuclear power station, we've mapped over 50,000 metres squared of formation. The important factor to bear in mind about this project is that the original fleet of nuclear power stations were built in the 1950s to the 1980s. And since then, we've had 25 years where we've not built any new nuclear power stations in the UK. And ultimately, we've lost our knowledge base in the UK. So therefore, this is the first one to be built, as I said, for 25 years. We're having to use external foreign experience in order to develop UK's knowledge base again, and particularly as we're starting the new fleet of nuclear power stations. So Hinkley Point C is located near Bridgewater, and it's directly adjacent to the Bristol Channel. Hinkley Point A, which is being decommissioned by Magnox, is directly to the east, and then slightly further east of that is Hinkley Point B, which is currently operational and is due to be decommissioned in 2023. The site itself is 1.75 kilometres squared, which is about the equivalent of about 400 hectares, or 245 football pitches, which makes you actually think about how big it is. So this is an aerial photograph of the site. It's separated into two halves. So sorry, that one. You've got the green lane, which runs halfway across the site. Now, the green lane is actually an archaeological feature, and it's a historic road, basically, which separates the site in two. The north of the site is where the main construction of the reactors and the nuclear power station is, and also where the construction platforms are. And the southern part of the site is actually a valley called the Holford Valley. And this is where all the material from the north of the site is being processed and stored. And when it's completed, this is what it will look like. The construction is actually of two nuclear power stations. This is Unit 1 and this is Unit 2. And we've got the nuclear island, which is where the two nuclear reactors will sit beneath the domes. And this is where uranium will react, a nuclear process called fission, in order to generate heat. And then the conventional island, and this is where heat is turns water to steam, turns turbines and generates electricity. And then this is the heat sink. The heat sink is where the water is then cooled down and then reused again around the nuclear power station. What you can't see here is that we're going to have 3 tunnels coming under the Bristol Channel. The 3 tunnels will be constructed using tunnel boring machines. 3 tunnel boring machines will be on site and ready for tunnelling next year. They're going to be 9 kilometres in combined length, 24 metres below the seabed, or the channel bed. The outfall tunnel, of which there's 1, is going to be 8 metres wide, and there's going to be 2 intake structures. The TBMs aren't actually going to be rescued at the end of the project. At the end of the project, they're going to be stripped down and then abandoned. Oh, sorry, I also forgot to say that the heat sink is actually the deepest part of the site. It's going to be 33 metres vertical faces from standing at the top. So the geology and depositional history of the site is relatively simple. So the rocks on the site were deposited in the southern margin of the Bristol Channel Basin, and they're Permo-Triassic to Jurassic in age. So it's about 195 to 250 million years ago. So this was when the UK was part of Pangaea, and it was in a geographical position similar to that of today's Sahara Desert. The sequence is the change from terrestrial to fully marine conditions, and this is caused by sea level rise and subsidence and inundation, crustal extension of the basin. The oldest rocks that we have on site are the Mersey mudstones, which is the red marls, part of the Mersey mudstone group. Now, we rarely see these on site. They're mainly at the southern part of the site, at the base of the Holford Valley, and only then when we dig, but we do encounter them. They're wind-blown dust deposits, many of you know, and hypersaline mudflat environments. And then these are overlain by the Triassic Blue Anchor Formation. Now, these are dolomitic siltstones, mudstones, and they're high in sulfates and vaporite deposits, and they're from tidal marsh environments. With rising sea level, these mudflats were inundated, and we've got a swampy, marsh, anoxic environment. And this is actually when we mark the change into the Penarth group, and we have the Westbury Formation deposited, which is like a black, shaly mudstone. And then we've got sea level still rising, and we have the formation of the deposition of the Lilstock Formation, and that's an intertidal zone, shallow water, but we've got grey-green siltstones and mudstones. Finally, we have the Blue Lice Formation, and now we're in fully marine conditions, depositing limestones and mudstones, which are the majority of what we see on site. So we have a number of geological processes that we're undertaking and supervising on site. So first of all, we have to develop a geological ground model to understand what's happening on the ground. This is from numerous ground investigations that have been undertaken through the years. The site then needs to be dewatered, mainly because the design assumptions have assumed that there's no water in the excavations. And so we need dry excavation conditions. It also makes it a lot easier, by the way, as well. As an excavation is undertaken, we start to get vertical sides and slopes. These need to be supported and require logging and assessing. And then these slopes, as I said, some of them are very high, or very deep, and the groundwater levels need to be monitored and ensure that they're stable and that the work areas are safe. When we get to the bottom of the excavations, this is where we're basically going to build our nuclear power station up from. So the foundations are actually going to be put directly onto the rock. These areas need to be mapped and logged because obviously they're important for nuclear safety. And then all this material needs to be removed. So all of the material from the deep dig area where the nuclear power station is going needs to be removed and processed and done something with. And then any unforeseen ground conditions, we need a ground investigation. Now, I'm actually involved in all of these processes that happen on site. I oversee the contractors and their designers while they're undertaking these processes, and I'm just going to quickly go through some of these processes now with you. So just to put into context, so I work for NMB, who are the client, responsible designer, and the principal contractor. We're what's described as an intelligent customer. And this is a term developed by the ONR, the Office for Nuclear Regulation. And it basically means that the client should know what's required. The client should know how to supervise and how to specify requirements and how to technically review the results. So that's what part of my role is. I supervise, I oversee and undertake independent assessment on all of the, well, most of the subcontractors' work. So I mainly supervise Geotechnical, who's our Tier 1 contractor for the enabling works, for the earthworks, and their principal designers or design consultants are Ikon and Golders. Mark, on the other hand, works a lot with Kenepe and Atkins and Bynol, which he'll describe a lot more later on. So first of all, we had to come up with a ground model. So data is collected from a series of historic ground investigations that have been undertaken for a number of years on site. I was actually involved in one of the ones in 2011 by Structural Soils. And all this information is put together by EDF and Geotechnical to create a preliminary ground model. So as you can see here, this is a cross-section through basically to the northern part of the site. This is the heat sink here. We've got the nuclear island is there. We call it the cake topper. And we've got the red marl, which, as I said previously, we don't see in the northern part of the site. The blue anchor formation outcrops in this anticline feature. We've got the Penarth group, which outcrops mainly in the galleries, but also at the southern part of the excavation. And then we've got the blue lias formation, which is the main area where we excavate, which is absolutely fantastic for us because it's also got the most consistent engineering properties compared with the others, and it's best for reuse. Now, I say that, but all of these lithologies have their own engineering geology challenges. Now, the geology might be simple, but the structural geology isn't. This is a drawing of the northern part of the site where the nuclear reactors unit's going. So that's going to be one, and that's going to be another. So as you can see, there's a number of faults that cross the site, and these vary in scale. They're mainly northwest to southeast. Some of them can have massive offsets, like, for example, this one, which is a couple of meters offset. And then some of them might be incredibly minor, like this one, where you see little or no deformation of the surrounding rock. We've also got an anticline feature, which is here, which is also offset by faulting. Now, both of these structural features are then vary our ground model, but also influence and change the weathering profile and also the hydrogeology. And at this point, it's also worth saying that the bedding is very consistent across site. It's all dipping towards the north by about 8 to 12 degrees, almost everywhere apart from that anticline feature. So first, we have to reduce the groundwater levels. So this was undertaken by Golder, who are Geotechnical's principal designer, and this was supposed to have started in October 2016. However, it was delayed because of discharge permitting with the EA, and also because we've got massive ongoing issues with perched water. This is mainly due to the structural geology as we've been excavating. Obviously, this is an effective program, but as the HPC geotechnical team, so the geologists from Geotechnical, NMB, Golder, and Ikon, we've worked together and we've come up with additional strategies to try and reduce that, including this, we call this the massive sump, the super sump. This is the bottom of heat sink 1. Is maximise dewatering, but also we've installed additional dewatering wells. The slopes have been designed by Ikon and constructed by Geotechnical. They They consist of sub-vertical faces. They're about 84 degrees, I believe, but when you're standing at the bottom of them, they look vertical. They're temporary, and they've got a design life of 10 years before they're being backfilled around the structures that are being constructed within them. So in total, there's going to be 112 kilometres of ground nails which will be installed, and these nails will measure between 6 and 14 metres long, depending on the ground conditions. But what I said about the bedding dipping north, when you've got north-facing slopes, we do have a lot of problems with internal corners. For example, we knew about this a long time ago. This is Hinkley Point A when it was being constructed next door. And if you can see that picture there, that used to be there. Large blocks from the limestone beds and the blue limestone formation do tend to fall into the excavation where the bedding's dipping towards the excavation. However, and we actually did discover that almost immediately. This is incredibly early on last year when we first started excavating. What we've managed to mitigate this issue by stitch drilling in order to prevent these limestone blocks from falling out and making it a lot safer. Now, due to the sheer number of slopes, we've mapped and logged almost 500 slopes so far, and we're only almost finished Unit 1. We're just starting Unit 2 now. Ikon needed to come up with a very simple method for mapping and logging these slopes. And what they did was they split the slopes into design slopes and matrix slopes. So design slopes are those that have got loading at the crest. For example, a crane sitting at the top as part of the construction process. These slopes have been modelled, and the design for the nail layout and the length of the nails have all been custom designed for that individual slope, which, as you can appreciate, takes a long time. So they came up with a design for something called a matrix slope. Matrix slopes are those where we don't have any loading at the crest. Depending on the orientation of the slopes and factors such as the GSI, the Geological Strength Index, determined from the mapping logging on site, the joints, from the joints and the rock strength, we're able to on site determine what sort of nail spacing and nail lengths are required there and then, and we can adapt that depending on what the ground conditions encountered are. When a fault is encountered, we've also got Ikon also came up with set nail patterns, and this is depending on the width of the fault and the orientation of the fault relative to the face. This provides a very flexible and efficient methodology, in which case any modifications can be done there and then while in the field. Ikon also contacted Bristol University and Atkins to discuss disturbance of the rock masses. So when we excavate in these excavations, we're using machinery. So we're excavating using a toothed bucket rather than blasting. And this can cause excavation damage behind the face. This causes a reduction in the rock mass strength, and it also allows for stress relief. Now, it's really important to verify and determine what this value is, because a lot of the time a conservative value is used or assumed rather than a realistic figure necessarily. So partnering with the University of Bristol, they undertook a series of geophysical investigations of the rock face to determine the extent of the disturbance of the rock when it's being excavated at different times during the excavation process. This had only been used before at research level or mainly in tunnelling, so it's never before been used widespread in construction. Geophysics was successfully applied, and they managed to determine the extent of the disturbance behind the rock face, for example there, managed to verify it, and then value engineer the faces, so it actually reduced the cost. Now before then, if you can see in this photo here, we've actually got these lines. These lines are called vertical dowels. So what we were doing before we had this information was drilling holes, bore holes, sticking bits of metal rods down them and grouting them up, and using them to reduce the impact of the excavators against the faces and to prevent over-excavation. By not having to do this, we actually saved £250,000 worth of material and labour. and 4 weeks off the construction process. Now, 4 weeks doesn't sound like a lot when it's a 10-year project, but when it's £1 million a day, it does start to impact. Now, these faces and the groundwater levels are monitored daily. We've got a series of inclinometers, total stations, prisms, and piezometers all around the site monitoring these slopes, monitoring these excavations to make sure that nothing is unstable. So any significant movements or rises in groundwater level are identified, and we discuss these during a daily meeting. Now, when Ikon designed these slopes, they allowed for acceptable movement, design movement, depending on the height of the slope, its orientation, and the amount of crest loading. So these are called triggers. We've got amber triggers and red triggers. Now, if any of the slopes breach these movements, then alerts are sent to the members of the SRG group via text message, which is very useful. We sign the permits daily, and if anything has occurred, we call emergency meetings, basically. And this is our formation mapping. So they have important nuclear implications for nuclear safety because the horizontal formations are going to form the foundations of the nuclear power station. As part of the ONR requirement, they require lifetime records because they directly affect nuclear safety, and they'll extend for the construction, operation and decommission life of the power station. So these are mapped and logged in detail by the key-bound geologists on site and then independently verified by myself and my team. And we look at the geology, the discontinuities and the georeferenced images. And as I said, all the material that from the deep dig, from the main excavation area has to go somewhere. So the whole site is generally a cut and fill exercise. So everything that's excavated from the northern part of the site is either processed and reused, either as backfill around the nuclear power station itself, or it's used for the construction platforms. And if it's not used for either of those, it's taken to the southern part of the site and used to backfill the Holford Valley. And by the end of the earthwork phase, which will be shortly, we'll have moved and processed over 5.6 million cubic metres of material. And I believe at the moment we're at 5 million cubic metres of material has been processed and moved around site. Now, it isn't as straightforward as it seems. The volumes for the reuse of the material and how we're placing it in the southern part of the site was all estimated from the preliminary ground model, including the weathering horizons, which is how we distinguish what material goes where. Now, obviously, the ground model, the preliminary ground model is changing all the time depending on what we find. And changes to the weathering profile and also construction issues, for example, handling deterioration due to exposure and weathering and trafficking over these areas means that the volumes of each of the materials that we need changes, sometimes detrimentally. But we oversee this and make sure that we minimise the impact as much as possible. Now, as I said, things don't always go to plan. So we need to be flexible in responding to unexpected ground conditions and unexpected features. So the size of the ground investigations we undertake varies greatly. So on a weekly basis, we could be doing trial pitting to establish weathering profiles, materials in the ground, rock strengths, particularly for new excavation areas to determine where they're going to be taken to. But sometimes other issues come up on site. So, for example, this is the dry dock constructed for Hinkley Point A. When Hinkley Point A was being constructed, they needed the dry dock to they built a caisson. And in that caisson, they constructed the outfall structure, which you can still see in front of Hinkley Point A in the Bristol Channel. But when they built it bang in front of the Hinkley Point C location of where we're building our current nuclear power station. We knew it was there. Obviously, we've got these photographs, but we didn't know exactly how it was being constructed. We didn't know that we had anecdotal information about that it was sheet piles. We didn't know how it had been decommissioned. We didn't know how it had been backfilled. We didn't know how deep it was. We didn't even know its exact location. So therefore, we undertook a ground investigation earlier this year to try and figure out a lot of this information. We'd been told that it had been backfilled using Land Rovers and bulldozers, and we had to verify whether that was true. The main reason we had to verify if that was true is because this was potentially in the direct alignment of one of our outfall tunnels. So we had to design a ground investigation that had that worked in parallel with the construction, particularly of the seawall that we were about to build on top of this. And also, when we were excavating one of the galleries in the southern part of the site, we came across dissolution features in the Blue Anchor Formation. And we knew from ground investigations that there was potentially this problem, but we didn't realise the exact extent until we dug down to formation level. We had to quickly find out about the size of these dissolution features, the connectivity, and the extent and depth of these. So we quickly designed a ground investigation, which has been undertaken, and a remediation design, which is now pressure grouting. And we've also had one failure on one of our slopes where it breached a red trigger. This is DE21 H10 slope in one of the southern galleries. And shortly after excavation, it's an east-west trending slope, so it's, the bedding's dipping into the excavation. There was significant movement and it breached a red trigger on a Saturday morning, as luck would have it. We quickly, as we work on the weekends, we quickly did a site inspection after the trigger breach, which was obviously text to us, and we found that there was a persistent discontinuity at the toe of where they'd just excavated, and that had caused the movement. So Ikon quickly got all of their information together and sent it off to their design offices to look at a remediation design. While on site, KIRBAM, NMB and Ikon tried to come up with a short-term solution to fix this, to make it stable, make it safe so we could carry on working in the area. We had to use the materials and equipment obviously that was on site in order to do this. So we came up with the idea for a toe berm to stabilise where they'd just excavated from, additional anchors and additional nails. And they were all installed on the same day. Within 5 days, Ikon returned the stabilisation design, and within 3 weeks, the area was completely safe, the slope was not moving, and we could continue working in the area. So I'll hand over to Mark now for about the detailed design.
Thank you, Gemma, and thank you, Richard, for the introduction. My name is Mark Scorer, Principal Geotechnical Engineer for Atkins SNCL, and I've been working on and off on Hinkley Point for over 5 years now. And I was thinking on the way up that this presentation, not necessarily intentionally, is a bit like a Tarantino film, not for violence and number of kills, but actually the sort of order of it. Gemma sort of started with the middle bit. I'm now going to take you back with a bit at the beginning, and then take it on a little bit further, post the enabling works and more of the construction. But that's probably where the similarities end, so sorry to disappoint you on that. So just to reiterate sort of the approach and the organisation structure, most of the work that Atkins have been doing on the design packages have been through CANEPE, a part of NMB, and the client as EDF. Their focus often is on the plant and the mechanical fixings inside these structures that actually make the nuclear system work. And we've been working extremely closely with Bylaw, who are the contractors for the construction of the site works, not just the enabling works, which is more KIRBAM. So Atkins' involvement on and off has been for the last 10 years, since 2008, provided a number of services that you can see up there on the screen. And from a personal and geotechnical point of view, some of the things that I'm going to touch on tonight are the seismic and geotechnical engineering, some of the civil engineering, the earthworks, and also go a little bit beyond, as I mentioned, into the structural design and some of the digital tools that we've been developing at Atkins to increase efficiency and help delivery on site. So the first actual involvement that I had was reviewing the final geotechnical interpretive report that was produced by TEG, the designers from EDF, on behalf of the Office for Nuclear Regulation. And I think at the time then, I certainly didn't anticipate that I'd be looking at that document significantly for the following sort of 4 years. But in reading that, and it was a very significant document, which has now been subsequently built on by Gemma and the team with subsequent investigations to fill any gaps. But at the time, it's certainly become the Bible almost for where we've been looking at parameters and developing them. Following that, we've picked up a number of design packages, over 8 kilometres of technical galleries which run all around the site. These include the drainage gallery, which runs around the periphery and forms the permanent drainage solution, including relief wells, all of which had to be seismically qualified. 2 main packages for the conventional island, so not actually the nuclear reactor, but you've got the unclassified buildings and the classified buildings. They are colour coordinated, so as you can see here, the blue buildings as the unclassified include sort of the turbine island, and the classified include sort of the heat sink and structures that do need to be fully seismically qualified. There are different grades of seismic qualification that are required. We've also done a number of buildings from developed design stage and value engineering, and also done significant other 3D reinforced concrete detailing. And I'll show you a little bit later as how some of the tools we've developed has helped us win that work. And I think it's a total of sort of 750,000 metres cubed of reinforced concrete in the structures at the end that we'll have designed, so it's not an insignificant amount. For the majority of these building packages that I just mentioned there, they each begun with the structural design method statement. And whilst it's called the structural design method statement, there's a lot of input from various different disciplines. And from a geotechnical point of view, the areas highlighted red is mainly where we interface with our structural colleagues and also the contractor as well to what we can do. Because this happens at the beginning, often it's more about process, about how we're going to do things, and for those of you who've worked in the nuclear industry, that's almost just as important as the actual information that you're going to use. You need to be transparent on how you develop that information, the parameters that you use, and where it all comes from. And so various inputs from developing a ground model, deciding on the seismic design, whether we're going to take a single profile for both Unit 1 and Unit 2. Construction considerations, Gemma talked quite a bit about the backfill. There's a significant amount of material that's coming out of the ground. Reuse was a key factor of as much as that material as possible. And to use that as structural backfill, it's got to meet certain criteria. And certain parameters that we need from an engineering point of view is a key issue. Actions and combinations, there are a vast number of load cases to be considered, not just seismic, but also maintenance, water levels across the site, and how they fit in with our analysis is important early on for a collaboration with our structural colleagues. The software that you're going to use early on as well, you need to identify, develop a verification and validation report which demonstrates that software is fit for purpose. You often need to define an analysis methodology as well, which, as I'm sure many of you will appreciate, sometimes at the beginning of a big project, you don't know exactly how you're going to do it, although you know you can do it. Things evolve over time, you meet different challenges, but this provides a good opportunity to get your thoughts down on paper and provides clarity for all parties involved so they can see how you're going to do it, and any objections or concerns can be raised by the relevant stakeholders. And that, again, is crucially important in the nuclear design process. And, of course, your limitations and assumptions are vitally important. One of the really positive things that I found on this project was the early involvement with the contractor, in this case Bailo, which is a joint venture between the French contractors Bourget and Lang O'Rourke. And getting them involved early, and we actually had a member of their team sitting in the design house. It really did benefit the project, and I know often it's preached about early contractor involvement and engagement, but it really did make things much easier, especially for sequencing their planning, their construction, if that can be fed early on into the design and analysis, especially from a seismic point of view, which can be quite lengthy and time-consuming. Models might take sort of a week of runtime. Then if you know you've got the right parameters and as close as possible as to what you're going to have on site, then it gives everyone reassurance. So that is something that has worked really well on this project. The next stage, and sometimes in tandem with those structural design method statements, is again revisiting the ground profile that Gemma's discussed and the geology that I'm not going to rehash in this case. But from our point of view, it's taking it that one step further and really nailing down those parameters that are key to not just the static designs that we're carrying out, but also the dynamic material properties. In the case of seismic design, we're really interested in the shear stiffness, basically, the shear modulus, and how that might degrade, again, with the damping coefficients. And there weren't, unfortunately, any degradation curves, which you can see here for both how the stiffness degrades with strain over time, if you imagine through an earthquake, how your stiffness varies. And so we utilized some from the literature. Davis et al. Had developed site-specific for Hinkley Point back in the 90s. And we've also then for the backfill material, which is an interesting type of material, being site one. As Gemma mentioned, it can degrade over time, and therefore its long-term behaviour is not necessarily consistent with its short-term. And so there's some of the considerations that we needed to take on board when we're putting them into our seismic models. And we used relationships developed by Darendale and Stokey et al. And how it varies with plasticity. You can see the earlier degradation from the low plasticity material. These relationships were key because they're used in the development of the time histories. There are site-wide time histories, and we take those site-wide time histories that are developed for the free field at ground level, and what we do with them, effectively, we deconvolve them through our ground profile to our assumed bedrock, and then use those as input into our detailed geotechnical model to run the seismic analysis. In this case, we were doing it in FLAC 3D. So that's the first stage, which once we've got a defined ground model, we can do. The seismic soil structure interaction was a big part and a crucial part, and just the first stage of an interaction with our structural colleagues, and part of the process that I'll show you later towards what we all want at the end of the day is actual detailing of reinforcement for them to construct on site. Sometimes it's easy to lose sight of why you're doing things, and we are here to actually construct things. And so it's an important first step. And it was our structural colleagues first that would develop an explicit, detailed, full 3D model of the structure down to openings of less than 0.5 of a metre. So it's a very detailed, massive model, not something that we could easily run in our geotechnical software with a complex soil. So we simplified the model, and then we constructed that model in our FLAC 3D software. And the first step of that was then to validate that the simplified model behaved as the full explicit complex model did of the structure. So then we knew that every analysis that we performed to get the soil structure interaction could then be taken forward and the inputs provided to the structural model, which could then be run with over 1,000 different load cases to get the reinforcement demands. You can see a comparison there of what we did. They're not the same model, I promise you. The bottom one is the structural model in Abacus. The top one is the FLAC representation, and the contours are the same scale. And this is just a comparison that we did to a 1G lateral load, and it shows quite clearly that the comparison is a good one, and we could trust our structural model that we were using in FLAC. We would then, in FLAC 3D, add the ground, which is the important thing from a geological geotechnical point of view, even though some of our structural colleagues don't always believe that. And this was our model. It's got free field boundaries at the edges, and it had a quiet base at the bottom. where we would input the time histories. These models would be run for a number of sets of time histories and for a number of different soil profiles in order to bound the problem in accordance with the nuclear codes. You look at a lower bound and an upper bound soil case with a variety of time histories to capture the nonlinearity that you might see in the soil. It was used to produce response spectra and seismic soil springs. These soil springs were then directly mapped because the models were set up the same, could then be mapped directly from FLAC3D into the Abacus model, providing a good interface with our structural colleagues, and they could then use the input motions and also the seismic soil springs with the explicit structural model to then run through multiple load cases and get the demand for their reinforcement needs. For the technical galleries, we had to adopt a slightly different approach, given that there's over 8 kilometres of these, and they are highly variable, not just in their shape. There were single, double galleries, overlapping galleries, but also in their depth of burial, varying from sort of 15 metres, I think, was the deepest, and then overlaying with backfill. So we needed to take a more bounding approach that wouldn't require each segment to be individually designed throughout the site. These galleries, for those of you who aren't aware, are actually large tunnels that around the whole site that allow the vital mechanical, electrical and process services to be encapsulated in and designed around the site. And the goal was to basically maximize off-site fabrication and sub-assembly so they could effectively be brought to site and dropped in place with minimal fuss. But again, they had to be seismically qualified. We took two different approaches with our structural colleagues, looking at both a displacement-based theory and force-based to accommodate or basically account for the maximum displacements that we were going to get in the soil. And we did that in quite a straightforward way by looking at, if you like, the stiffest profile that we thought we could come across around those 8 kilometres on site, regions away from the faulting, and then also bounding at the other end, areas where there was highly faulted and fractured, where we might get a significantly lower bound case. And we ran a series of 1D analyses in shake, and we looked for the maximum soil strains and maximum displacements that we found in the ground profiles based on varying thicknesses of fill. By doing that, it enabled us to bound the problem from a structural point of view. They were able to convert them into displacements and drift ratios, and effectively design limiting cases for the galleries all around the site in quite a quick, easy way. The technical galleries was quite a milestone for the project because it was the first piece of nuclear concrete that was poured in, as Gemma mentioned, over 25 years in the UK. So it was quite a big deal for the project here, and it went down well as a general milestone for all involved. A number of parties. This doesn't happen just by a single business. There was Canepe, NMB, obviously by law the contractors, and the consultants as well, and it was a good team effort. Some of the digital tools, which is really, I'm now going to sort of extend and go beyond, I guess, the remit that I've been purely involved in from a geotechnical point of view, is these beneficial digital tools that we're quite keen on at Atkins to try and automate some of the interfaces, not just in the geotechnical point of view where you've got a lot of data coming out of our model, mapping across to a structural model, but also then taking it forward to reinforcement designs and detailing, and with a view to sort of paperless construction on site, which we're currently trialling, and it's improved efficiency a lot. We're not quite there yet, but it's definitely improved thing. I've got a couple of videos which I'll show you, and hopefully they work. One of the tools is Contour RC, but this just gives a little introduction to the design process, starting from the geotechnical and the seismic soil structure interaction through to actually the purpose and the detailing of the rebar. So we'll have a look at this. This was our FLAC model, where we're doing this seismic soil structure interaction. We've got the ground, we've got a simplified structure, and we're running a number of time histories through. We've got a nonlinear backfill to see how the structure responds. And then that's transferred to Abacus. You'll see this is the explicit model, a lot more detailed, includes every single wall panel element in the design. That's run with all the different load cases, maintenance, water, all the different loading there, and you can see some of the mode shapes, the rocking and the translation. That's then taken forward into a tool that we've developed called Contour RC. So this enables the user to select a panel. They can look at the theoretical reinforcement that's required. Then with their knowledge, they can select areas where the demand is higher and where the demand doesn't fall within an obvious reinforcement need. They can highlight those areas, specify the requirements, whether it's C32s, 200s, to get the required utilization ratios up. And then they can output that directly, so the contours therefore not only show the theoretical, it's then taken forward to a practical and then an actual reinforcement that's required in those elements. That can be exported directly in a number of formats as reports, and so you can get a lot of the information that's crucial to the detailing, which is then detailed up in a 3D fashion now. This enables every single reinforcement bar to be plotted, declashed before it actually meets site, and these all to be manufactured before it gets to site. So this means there's a lot less requests for information and field consent requests, and I'll show you on this sort of flow chart basically what was shown on the video there. So we're taking the model, we're getting the reinforcement requirements, we're outputting the final plots, and then we're fully detailing it up in a 3D model. So everything, and this has reduced the RFIs for the technical galleries, which is 1.5 kilometres already constructed. We've only had one potential clash, and that was actually with a water bar, not reinforcement. And given other projects that we've worked on where previous 2D reinforcement drawings were being utilised, it's a fairly significant win and time and cost saving. That flowchart shows the virtual fixing that we can do. So we run through the flowchart there. As I mentioned, it's any potential RFIs or field change request in the 3D environment. You can do it in the model on site with all the interfaces of pipeworks, fittings and fixtures. The materials can be ordered directly from the model. The drawings can then be reproduced directly from the model. Any changes, things like that can be taken through, and it's really helped the efficiency and smooth the process on site so far, working with the contractor. And this is a final fly-through of the Tekla model that we've developed, effectively the 3D reinforcement. This is every single bar in the technical galleries. You'll see as it flies through every link as well, in areas of potential clashes with staircases, with embedded features, which is often a key area for where clashes happen, so anchors and things like that. It can include all of those. You can see the staircase there as it flies through. I think there are over 2 million bars in this model, which ordinarily would have to be done in drawings and then exported and often declashed on site. And then this shows the interface with the heat sink structure, and you can see all the interfaces with the pipework that can be accurately detailed prior to site, and it's reduced any clashes to, as I said, one so far. And you can see the complexity of the galleries there as well, with overlaying and cross galleries and double height galleries, which is why we did need a simplified solution from a geotechnical point of view. As I mentioned earlier, the goal long term is to move towards paperless construction. We're moving in the right direction. Digital tablets on site. The reconstruction is being trialled as we speak, and we're getting there for the 3D reinforcement detailing. We've won an award this year from the UK Tech Awards, and it's now gone through to the Global Awards for all that modelling that our colleagues have been doing on site. So it's a really positive step and been really well received by the contractor. Another digital tool that we've used from more program management and project management point of view is Ikon. It's more of a coordination platform because we had 3 large packages, the technical galleries, the classified buildings, the unclassified buildings. We found that by having, if you like, a site layout and a lot of big data behind this, we were able to store in this model all of the early warning notices, all of the technical queries, all of the deliverables, and we could chart the progress of each building through from its program, its progress, the percentage delivered, just by clicking on each building or clicking on each package and segment, and it provided a really useful tool, not just internally to manage the works, but also from the client's perspective, they could see what we were doing. And the work with Canepe, that brings me on to, is that there were challenges early on, as with any project, but the one thing and the real significant change happened when we had a member of their staff come over and sit in our design office, and we had staff go over and sit in their office. When they were working side by side, they could see the difficulties and the challenges that we were having, and also vice versa, and especially being a multinational client with different expectations and understanding of how the regulator works in this country, it really was a key turning point to where we co-located. And so I'd certainly recommend that for projects going forward. That just about brings me to the end. And one thing that Gemma touched on initially, but just like to reiterate here, is that we are just small pieces in the jigsaw of this vast project, and these are some of the supply chain partners for EDF that without which it wouldn't be possible. It's not a one-man job. It's certainly a vast undertaking from a number of different customers and clients there, which are all pulling together. The shared values from both the project values on the left-hand side of Hinkley Point in terms of clarity, respect, humility, positivity and solidarity tie quite well with the Atkins SNC values of safety, integrity, collaboration, innovation. And these have been at the key and at the core of the work that we've done both on site in the design houses and with the contractors. And I think it's been carried out, and I know the work on site has been carried out in good spirits and with those key values. Other than that, I think it's just thank you for listening, and if you do have any questions, please feel free to ask.
As we are broadcasting onto the internet, if you do have any questions, please wait until the microphone reaches you and use it to speak into. Does anyone have any questions?
Yeah, I'm John Woodsford. My question concerns the timeline for this project. I'm not aware of it. But during the design and construction of this project, and bearing in mind the Japanese nuclear meltdown, was there any need to retrofit or change the design of this project to account for the learnings from that Japanese disaster?
I can certainly say that there wasn't necessarily the need to retrofit. A level 2 design had been undertaken. The timeline for following the Japanese disaster, which was obviously a hot topic for the ONR, was the reports were fed into the project and were reviewed, and any potential redesigns that were necessary, and none that I'm specifically aware of, were accommodated within the timescales. I mean, we're still, whilst Gemma has been on site for 2 years, the design of many of the key structures at a detailed level were sort of post that. And so given the events of the Japanese disaster, which was a couple of years before that, I believe they have been incorporated as necessary, but there was none specifically that I was aware of. Lessons have been learnt from it, definitely, but in terms of the actual details that we had, there were emergency response centres that are being designed at this stage, are taking into account any lessons learnt from it, though.
And I can't give any specifics either, but from the trainings that I've had undergoing advanced training for the EPR design, I know that they took a lot of the lessons learnt from Fukushima forward, and have used it as part of the design. There have been quite a few changes right at the beginning of the construction for it, but again, I can't give any specifics.
Thank you. Anyone else? I've been told actually the microphones aren't working, so. Yes.
Without the microphone.
Yeah, we don't need them. They're not working until we don't.
Ian Long, BRE Associate. Question concerns sulfate pyrite, which of course was an anticipated problem for concrete.
Mm-hmm.
Can you tell me what procedures are being used for monitoring, for logging sulfate pyrite during construction, and is the same being done in the extensive stockpiles that are going to be used for backfill for concrete?
Yes. So we have a lot of pyrite in the Westbury Formation, Little Stock Formation, to a lesser extent in the Blue Lies Formation. One of the procedures for reuse, material reuse, is that the stockpiles are, well, the material stockpiled separately, particularly the Westbury, and it's stockpiled and exposed for up to 6 months in order to naturally let the pyrite weather out before it's processed and reused.
Weather in 6 months.
Sorry?
It won't fully weather in 6 months.
Some of them, you'd be surprised, even some, well, the formations themselves are only allowed to be open 48 hours because of the rate of disintegration on the surface that we experience anyway. But also, you might know this more than I do, but the concrete's specifically designed to meet those, the interaction with pyrite. So
there are additional protective measures. Additional protective measures that are employed in the design, whether it be sacrificial blinding concrete, whether it be membranes, to accommodate and account for the potential aggressivity towards the concrete.
Yeah, but I understood this in the stockpiles, the oxidation was to be minimised as much as possible, to stop the air getting to it, not to expose it and let the pyrite oxide. That would take the sulfate class up to 4 as a minimum. It's not wanted.
I can't answer that question, I'm afraid. All I know is that we stockpile it for a minimum amount in order to try and reduce the amount of pyrite that's in there by allowing it to weather out.
In the Blue Lies?
No, not the Blue Lies, that's mainly the Westbury. And the Westbury doesn't...
Well, I understood the Blue Lies was one that's going to be mainly used for that.
It is going to be mainly used for backfill, but we have minimal levels of pyrite in the Blue Lies Formation that we've encountered. And then, as Mark said, there's additional procedures in place to prevent it interacting with the concrete.
Yeah, I understand that, protective measures.
Yeah. Phil Marshall, interested in your 3D visualization of the reinforcing bars.
Okay.
To avoid clashing between the bars. Did that model also enable you to optimise the aggregate size in order to actually achieve adequate placing of the concrete?
I couldn't tell you if they also used it for that, but they would have at least used that as a guide, because as you can see, they're quite congested.
Yeah,
A lot of the, yeah, absolutely. And so it was. They were limiting aggregate sizes and to ensure that the concrete could be poured and vibrated to make sure that it's not just effectively a steel mass wall. So yes, it was taken into consideration, and minimum sort of spacings will have been used for that. But yes, it is fairly congested, as you can see from what those gallery walls are typically 700 thick. So there's not a lot of space in there, but it will have been taken into consideration for that.
My name is Christopher Botiellis, and I would like to ask you, what are the seismic design assumptions with regards to earthquake magnitude, ground acceleration, and the event of a tsunami?
Okay, so the peak ground acceleration that typically you're designing for in the UK is 0.25 G. So whilst that is not a high level of seismicity, it's fairly significant for the UK, given our effectively low seismicity here. For beyond design basis, that increases to 0.4 G, which is a high level of seismicity, as I'm sure you appreciate. And so we're fairly well covered, I feel, from a seismic ground acceleration point of view, from that way. And in terms of tsunami, I couldn't comment on what the hazards were for the tsunami that were considered. I wasn't involved in that process, but again, I imagine it was a fairly rigorous return period for a fairly large tsunami being based, as it is in proximity to the coast.
Have you also taken into account accidental impact?
Yes, there's sort of aircraft impact and things like that. All of those factors are considered in the potential hazards, accidental flooding, other impacts. But aircraft impact is one of those that's considered.
Stuart Baltimore from Atkins. Question for Gemma. The ground anchors you put into the wall, did you actually put in instrumentation to see how the load came onto the anchors?
Yes, we do, and they've also got triggers that we monitor. This is more Atkins look after. Ikon look after those and specify them, and then they're monitored by KIRBAM. So they're along with the face monitoring, the inclinometers, the piezometers, and the anchors. They all form part of the triggers for the breaches, and they're monitored daily. And if anything were to happen, exceed their design limits, then they're all sent via SMS to our phones.
We used to try and get hold of that data if it's possible for the British standard. I sit on the committee for it.
Okay. I'll put you in contact with a few people.
You didn't mention value engineering, and I was just wondering, given the inexperience of this type of work in the UK and the risks involved, whether it was actually taken on board or part because of the risks involved.
It's a fair question. Good one as well. No, I would say it was accurately taken on board, and there was a conscious effort. Obviously, with nuclear structures, there's less potential leeway for new design developments and things to be sort of readily taken on board. It's quite rigorous. It's quite code defined. A lot of them follow the US codes in the absence of any sort of up-to-date UK nuclear codes, given the fact that Eurocode specifically excludes nuclear structures, Eurocode 8 for seismic design. So the design was done in accordance with ETCC, the French code, which is largely based on ASCE 498 and 4305. And so we did, using those. It perhaps wasn't as easy to provide value engineering as on some other projects, but for a number of the smaller buildings as well, some of the ancillary structures, the design development that we've been able to get involved in from an earlier stage, so where we've got involved from a concept stage, not just brought in as the level 3 detailed designer, which we were for the unclassified buildings and the classified buildings. We had more scope to conduct phases of value engineering and have a look at potential benefits by either combining buildings or reducing their size and scope. And I guess recently that's become more evident for me as the projects looked to reduce costs going forward as well, and it's become a more important issue than it was perhaps at the beginning, which I think is fair to say. But yeah, it's definitely been taken on board and not just parked.
Sorry, it's John Perry. I should have said my name at the beginning. But did you actually do a lot in the end?
For the most recent building that I've been working on, yes, we have. We've combined buildings. We've reduced the size of it. We've reduced the size of the elements because, as I mentioned, we got involved at an earlier stage in the design process. For a lot of the buildings we were doing, we were brought in as a level 3 designer, almost, and just to ratify the design and detail it and ensure there wasn't any issues with soil structure interaction things. And there it's a lot more difficult because the design is further down the road, and it's much more difficult to make any significant changes. But where we've had the opportunity on a number of the ancillary structures, then we've been able to do some value engineering, and that was some of the most recent work we've done on the buildings.
I think I saw one over there.
I was just back to the sulphides found in the presence of pyrite. I was wondering what form the pyrite's in?
Sorry?
What form the pyrite's in?
From Boyle.
Yes, thank you.
Is any further work done after it's been stockpiled for 6 months?
We do chemical testing on it, and well, we test all of the stockpiles, in situ testing on and especially on placement of layers. So all of the layers that are placed, every single layer is tested to an extent, and we have ongoing chemical testing as well for all the placements. We've also obviously test all the water management zones as well for the water. Does that answer your question?
Okay.
Just quickly, testing's fine and you've got to do, but for goodness sake, make sure there's a geotechnical engineer looking at it.
Once again, KIABAM, and then it's overseen by NFB. So we have a direct hand, and we have to sign off directly on all of the testing that we see or that's undertaken.
What I mean is it's the observation. Testing is a very small sample.
Yes.
The observation is the important part as well.
Yeah. So we've got a wide surveillance team that do go out and watch placement of a select percentage of it. And we can see erroneous results when they've done it wrong as well. So.
Okay. Thank you very much, Mark and Gemma. I guess that brings things to a close this evening. If all has gone according to plan, there should be a drinks reception in the lower library waiting for us, so please feel free to join us for that. And once again, thank you, Mark and Gemma.